So yes, so this talk is about quantum state tomography, and this project was conducted in collaboration with Joran van Apeldoorn, Andras, Gilyen, and Giacomo Nannicini. And yeah, so when I'm going to speak about quantum state tomography, maybe the first thing I should say is what quantum state tomography is. And the quantum state tomography is the following thing. It is the problem of learning a classical description of a quantum state. When you have access to this quantum state in some way. And however you have access to this quantum state will determine how you in the end want to find this classical description. So there's two different settings in which you can examine this problem. You can either consider the setting where you have pure states, where you have a pure state that you want to estimate, or you can think about the setting where you can estimate a mixed state. So we're first going to have a look at pure states, and then the next slide we'll have a look at the mixed state case. So for now, let's suppose that we have a d-dimensional pure state, and we want to learn a classical description. We can make some assumptions on how we have access to this quantum state. So I have drawn three pictures here that indicate how we have access to our quantum state. So first, let's suppose that we have some black box which kind of spits out this quantum state psi. And all we can do is directly measure afterwards, do a computational basis measurement. Then all we can hope to do is learn like the vector of absolute amplitudes of the vector of the state that we want to learn. Secondly, if we have a black box which just spits out the state psi, but after we can do some quantum operations on it, then we can hope to learn the state up to some global phase. And if we get like a state like this, which we refer to as a conditional sample, then we can also hope to learn the whole state, including the global phase. And so before we started this project, what was known was an algorithm by Kerenidis and Prakash, which, if you want to estimate this vector up to L infinity norm epsilon, then you can do this in 1 over epsilon squared. And similarly, if you want to know it in L2 norm epsilon, then you can do it in d over epsilon squared. And also, it was a little bit folklore that there were lower bounds that matched this. So Kerenidis and Prakash gave a tight algorithm. So the first thing that we did in this project is we kind of closed the gap in between the L infinity and the L2 norm case. So any LQ norm where Q is in 2 and infinity, we tightly characterize like the number of times you need to call this black box. And you can see that this expression is very hideous, but we have like a matching upper and lower bound. So I cannot make it any nicer than it is. So this setting is very nice when you, for instance, are doing like an experiment in the lab where you only have this black box as some operations that you do in the lab and you don't really have more control over it. But sometimes you have a process where you have a little bit more control than just the black box which you can run forwards. For instance, suppose that you're running like an HHL algorithm where what you're interested in is like the final state, like the final state of your quantum algorithm. In that case, you have some kind of unitary which you can call, which prepares your state that you want to learn from the zero state, and you can also run this unitary in reverse. So this gives you a little bit more control over learning your state psi than just running a black box and then doing measurements afterwards. And so what we do in this project is we have a look at what this more control, this extra control that you have, what this can do for your complexity. And indeed, you can see that, for instance, in the L2 case, here you have a complexity of d over epsilon squared, and we show that you can do it in d over epsilon. So you get a quadratic improvement in terms of the precision. And also you get an improvement in the L infinity case and in the intermediate cases, but again, it gets a little bit messy. So this is the first part of the results that we've obtained. So this was the pure state case. Now, in the second part, we have mixed states. So mixed states are just a probabilistic mixture of like pure states that you have with a particular probability. And before we started this project, again, there were some things known. So one thing that was known is if you have like a black box which outputs like a mixed state, and suppose that you can only use like call this black box, get a mixed state, and then like you can do some operations in a measure, but only after you have measured and done with everything, you can do again like your black box and do like a new measurement. So you only can have like one copy of the density matrix rho at the same time. In that case, like there has been like quite some long line of work that tightly characterizes how you can estimate this density matrix. And curiously, if you have like multiple copies of the mixed state at the same time, then you can do better. So like if you can do like entangling measurements between multiple copies of your density matrix, then you can like do slightly better in terms of learning this state up to trace distance. And in this setting, we have looked at kind of at a similar improvement as what we considered in the previous case, which is like, suppose that we don't get like, you know, copies of this mixed state, but we get copies of a purification of this mixed state, and we can prepare this purification with a unitary and also call it inverse. And also in this case, we kind of show that the epsilon squared dependence that you have in the trace norm case, we can improve to like epsilon. So we get like, again, a quadratic improvement over the in terms of the precision. And additionally, we also characterize like the query complexity when you want to estimate this density matrix up to a different Schatten norm compared to the trace norm. We also investigate like the Frobenius norm and the operator norm. So this kind of to give you an overview of like all the like results that we obtained, but I haven't told you yet like how you do actually all these things. So what I'm going to do in the remainder of this talk is I'm going to focus solely on this square here, how you can do like mixed state estimation using this axis model here. So, and there's like 3 core ideas that go into like the algorithm that we design. And so I'm going to go over them one by one. So I'm going to list like the 3 core ideas that go into it. So the first idea is like, we consider the problem of learning observables, which is the following thing. Suppose we have like M observables, all like with a nice normalization of 1. And what we want to do is we want to learn these quantities. So we want to learn, you know, the inner product between like the state psi and then the observable and psi again. Now this is like a well-studied problem. If you just get copies of your state psi, you can do like a shadow tomography, as we saw in the tutorial session of QIP last year. You can do this in like log m over epsilon squared, number of times of calling this black box. And here again, if we consider like this stronger axis model, it was known that you can get this epsilon squared down to epsilon, but you pay a little bit in terms of like the norm of the observables that you're dealing with. And this was like a work by Hutchins and Wan and others. And what we have done here is we have improved like very slightly on their algorithm. And the way that we do this is we define a function f, which kind of takes an inner product with some arbitrary like vector x. It takes an inner product with like the vector of things that you want to learn. And this function, like we give an algorithm that computes the value of this function in the phase. So we give like some kind of block encoding technique algorithm that computes this function. And then we use like the gradient estimation algorithm to estimate the gradient of this function, which is exactly the vector that we want to learn. So this is kind of like a very little overview of what we have done, but like this is it has like a very technical analysis. So this is where the most of the technical work of our paper goes into. And so then, like the question is, okay, you can learn these observables in like this number of queries, but like how does this relate to learning this density matrix, which is in the end what we want to do? So suppose that this is our density matrix, and we have like the ij entry here. Then what we can do is we can define these 2 observables that where if you now compute like this expectation value, you see that you precisely get like the real part and the imaginary part of this one entry, of this ij entry of the density matrix. And now if we kind of compute this thing, so if we compute like, you know, the norm bound that we get from our algorithm, we see that we get exactly d times the identity matrix. So what we get here is like square root d over epsilon. So kind of by listing all of these observables, we are estimating each of the entries one by one, and hence we get like an entry-wise estimate of our density matrix with square root d over epsilon number of calls. So then, like the question is, okay, we have like an entry-wise precise algorithm. So how does entry-wise precision relate to having like precision in other norms, like in operator norm or in trace norm? And so one thing that you can imagine is like if you estimate each of the entries individually, like if you overshoot in all of the entries, so all of the entries are like epsilon too big, then like the operator norm of like your difference matrix, like the error you make will be like a matrix which is full of epsilons everywhere, and its operator norm will be epsilon times d. But it's very unlikely that all your entries will be epsilon too big, right? Most likely you will get like something which is a little bit over and something that's a little bit under. So you get like all kinds of different signs. That's at least what you would expect. And so to make this formal, what we should do is we should say that not only we are estimating each of the entries individually, but we're estimating each of the entries unbiasedly. So that like if we then then we can make like the statement that some entries will be under and some entries will be over. We can make that more rigorous. So what we do here is we kind of take this algorithm, and on top of this algorithm, we also want to make the estimation procedure unbiased. So in order to explain how this works, I'm going to go like a little bit, to a simpler setting. I'm just going to consider the phase estimation problem, where you have like some state and you have a unitary acting on it, and you know that this state is an eigenstate of the unitary, and you want to measure the eigenphase. The standard approach, the standard phase estimation algorithm, gives you a finite output set and then some probability distribution, which is kind of peaked around like the real value of what you want to compute, but it's a bit chaotic. It decays a little bit chaotically on the sides. And because it decays quite chaotically, like there's some bias here. Like if you compute the expectation value of this distribution, you're not exactly going to end up at like the value that you want to compute. So how do we resolve this? Well, there's a trick. And this trick is not ours, it was already present, but we kind of use it in a novel way. And the trick is to just take your unitary operation, take your unitary and multiply by a global phase. So just like randomly rotate the circle that you see in this picture. And then what that's going to do is like, you're not going to measure phi, but you're going to measure phi plus this extra rotation that you have been doing. And then after the procedure, you kind of turn the circle back again. But this rotation that you do can be any rotation whatsoever. So now your output set is not going to be discrete anymore, but you get like a nice continuous probability distribution. And the nice thing about this probability distribution is that it's kind of centered. It's symmetric around like the phase that you want to compute. So now you can kind of already see that you get something which is unbiased if you interpret the output to be on the circle. And if you want to estimate phi individually, then you have to cut open the circle somewhere. So you have to do some extra tricks. Like you have to kind of do some amplitude boosting by like running this several times and then like taking like the median of the outcomes and stuff like this. But these are all like classical tricks. So, and then if you do that, you get like an exponentially small bias from like opening the circle somewhere. Okay, so using all this, we kind of like take this idea and like put it in the gradient estimation with algorithm, which is non-trivial by itself, but you can like, like there's some details to think about here. But once you do this, you can kind of, we now get this entry-wise estimation where each of the entries is estimated unbiasedly. And then you can get like a operator norm error, which is square root d times epsilon, rather than d times epsilon as you would get naively. Okay, so that's the second idea. And the last idea is a norm conversion, which is the following thing. So what we have done now is we have designed an algorithm which can estimate our density matrix up to operator norm epsilon. But we also know that both of these things, like whatever we are estimating, the density matrix, and like our estimate itself, they have trace norm at most 1. So like the Sutton 1 norm of the difference will be by the triangle inequality at most 2. So, and remember, like these Sutton norms are just like the norm of the vector of eigenvalues. So in particular, I can take like the spectrum of the difference, like the error that we're making, take all the eigenvalues, and then kind of, the norm, the LP norm of this vector is the Sutton norm. And what I can do is I can draw this vector, I can draw where it might be. And because I know that like the L infinity norm is at most epsilon, I know that it is in some kind of ball. But now you can also see that there's kind of like a regime working. So like if your epsilon is very small, then this hypercube will be completely contained in this like L1 bound. And therefore, like the best you can do, like the best, for instance, L2 bound that you can give on your vector lambda is going to be just what you get from the Hölder's inequality. Whereas, like, if your epsilon is a little bit bigger, then, like, you know, if you grow the size of this hypercube, then the corners of it will at some point start sticking out from like the L1 ball, and once that happens, then you have some different points which are like the worst case for giving like an L2 bound, and hence you can like your L2 bound can get a little bit better than what you would get from the Högling or Hölder's inequality. So kind of, you can see geometrically here that there's something interesting happen, that you have like two different regimes. You have a low precision regime and you have a high precision regime. And these two bounds you can kind of merge into one statement, and then you get something like this. So you can see really that like this minimization is somehow like a consequence of like this geometrical picture of like having two regimes, like a small hypercube and a big one. So I just want to mention that kind of like this idea of like having these two regimes, having like a low precision and a high precision regime, is not only the case in this mixed state case, but it's also the root of like where all these regimes come from in like the pure state case that I mentioned in the first slide. And I also want to mention that if you give like a lower bound proof for this problem, you also have to consider these two cases separately, and you have to use like the same geometrical picture. So this geometrical picture really like exactly capture what's going on, not only in the algorithm but also in the lower bound proof. Okay. So now let me kind of recap a little bit, like the three things that we've done. So this is the setting that we have, and what we want to learn is this density matrix. So the first thing we did is we used this learning observables problem to give an entry-wise approximation of the density matrix that we want to learn. Then we used unbiasedness to show that each of the entries we kind of learn without bias, and this gives us a better bound in the operator norm. And then we can, using this like norm conversion with the two regimes, we kind of turn this into an LQ Schatten norm bound. And now, of course, we want to set this thing to epsilon. So then, like, we let epsilon prime depend on the precision that we want. We plug it into like the cost that we had earlier, and then you get like this hideous-looking bound of like the first type. So I hope that like this overview at least gives you a little bit of an idea of like where all these terms of this complexity come from. Like the fact that you have two regimes, that this comes from the geometrical picture. I hope that says a little bit more than just staring at this complexity at face value. Okay, so let me quickly summarize. So what have we seen? I have told you about the results that we obtained, like the complexities for a pure mixed state tomography. I have told you the three techniques that went into the estimation of the mixed state case. And there's a couple of things that are in the paper that I haven't mentioned, which is first is the algorithm for the pure state case. There's also like some tricks going in there that I haven't elaborated on. Then we also make some claims about the time complexity. And of course, there's a whole lot to say about how to lower bound, how to prove that these algorithms are optimal, that I haven't gotten into. And finally, there's like two open problems. One is like, in the mixed state case, there are still some like other norms that you can consider for estimating the density matrix. So these were all the dashes in the table that I showed you. So that would be interesting to look for if there's a better algorithm you can do there. And this is the most interesting thing, I think. What if you have like a unitary that you can only run forward, but you do not have access to its inverse? Like, do you then get an optimal algorithm? Does it have like 1/epsilon scaling or 1/epsilon squared scaling? Like, we have thought about this quite a lot, but we have no idea. So if there's anyone here who would like to, think about this, then I would very much be happy to have a think about that. So that's it. Thanks.
Great. You are right on time, and apologize for announcing your name wrong.
That's okay.
Okay, so do you have any questions? Oh, there's one.
Thank you.
Oh.
There's another one.
Thank you very much for the nice talk. So is this important? Like, I don't know any example where you would know how to run the circuit, but not how to run the inverse, right?
Yeah, I guess it's more of a like it's more of a philosophical question. Like,
okay.
like where does the power come from? Like, in order to obtain this improvement from 1 over epsilon squared to 1 over epsilon, like, do you like? Is it just the fact that you have access to the unitary in like some kind of controlled way, or do you really like fundamentally need that you can run it in reverse somehow? Like,
Okay, thanks.
So yeah.
Hi. Thanks for a great talk. So what about other sample complexities with respect to other figures of merit, say the infidelity, that is not a norm?
Yeah, so that would also be interesting. Like we haven't particularly looked at this per se, so I don't know if these things are like completely resolved. But yeah, I would presume that like similar techniques you could use in order to.
I mean,
like,
people have looked at this infidelity thing because it's there are good reasons to do it.
I see.
Okay.
Okay.
Right. Thanks.
Okay.
Thanks very much. Nice talk. I missed some point. In the first step, the linear observables, you define a function fx. I wonder how do you compute the gradient of this function?
How we compute this function?
Yeah,
the one that, yeah. So there's yeah, we use some block encoding techniques for this. So kind of one core step that usually goes into it is like given such a vector x that you want like that you want to take the inner product with, you kind of like create a superposition which kind of where like. If you look at all the amplitudes on like cat0, like cat j, cat0, you want like the square root of xj to be there, and then kind of you can take these inner products. Yeah, I don't know. It's a bit difficult to explain without like writing down. So yeah.
But I suppose that would affect your time complexity if you choose.
Yeah. So the time complexities will in general be like worse than the query complexities, and also we don't have like good time complexity lower bounds. So like what we do in our paper is we just count the number of auxiliary gates that you would need, but we don't give any claim about if this is optimal or something like this.
Yeah.
So.
Yes. Okay.
Yeah, nice talk. Yeah, so I have a question between the non-inverse model and the sample model. So do we know any gap or any separation between the non-inverse model and the sample model? Because it looks like it's the stronger sample model, right?
So I'm not aware of any, but it might be that they exist, but I'm not aware of any.
Okay, thanks.
Okay. There was one more. There's one more? Okay. You have to throw it.
Square 4.
Okay. Thank you for a nice pass. I have one question about the one of the three techniques. Actually, if we consider we need to do tomography of the infinite dimensional quantum state, can we use the first technique to perform this? Can you use the first technique for the tomography of the indirect dimensional quantum state, including coherent or squeezed state?
Sorry, about the first technique?
Yes.
Let me go there. What exactly? What do you want to know?
I mean, there are some complexities about the models. Can we apply these complexities to the case of infinite dimensional quantum state?
Oh, infinite dimensional.
Yes.
Oh, well, I suppose if the dimension like doesn't show up in the I think it should be possible. But you would have to check whether this tilde might hide like some logarithmic factors, and you would have to be a little bit careful whether these things don't blow up, right? But I think it should be possible to port these techniques, at least in query complexity wise. Of course, like how it goes time complexity wise is a little bit iffy if you're working with like infinite dimensional states, and it's not clear like how you should count time complexity anyway. So yeah.
Okay, thank you.
Infinite dimension is tricky. Yes. Anyway. Okay, I think it's about time. If you have further questions, you could welcome to talk to the speakers after the sections. Thank you so much.